All right, Monday's lecture, Monday that would have been May 1st, it's now May 2nd, and this is the first time I've had a chance to come in here and get a lecture together for you. But we're going to talk about the rank of a matrix. Okay, so before we talk about that first, I want to define what we mean by the row space. Row space of an M by N matrix A. It is simply the subspace of Rn that is spanned by the row vectors of A. Okay? And so what I mean by row vectors, I mean the vectors that go along the rows, all right? So for example, let's make A be 2, -1, 3, 7, 8, 5, 1, 0, -9. Then the row space of A is the span of the set of vectors. I'm going to write them vertically and as column vectors, but I'm going to do 2, -1, 3. That's the first row. Second row would be 7, 8, 5. Excuse me, and the third row will be 1, 0, -9. Okay, so it's pretty easy to get a spanning set for the row space of A. Just take the rows of A, turn them vertical, there's your spanning set. Might not be a basis though, right? Because this certainly spans the span of itself, but they may be linearly dependent, so you don't necessarily have a basis, so we have to kind of work with that to get a basis, or work with that, do a little bit more work, I'm trying to say, to get a basis. And yeah, so I guess I just go ahead and say, so this is the span, this is a spanning set for the row space of A. Basis, just put A in row echelon form. Non-zero rows will form a basis of the row space of A, okay? And so I think I will do an example here, but before I do that, let me just go ahead and make a note here. So, in row echelon form, number of non-zero rows equals the number of pivots, right? Because each non-zero row begins with a pivot. So that's the number of pivots. So that's equal to the number of pivot columns, which is equal to the number of vectors in a basis for the column space of A. All right. So the dimension of the row space of a matrix A is equal to the dimension of the column space of A. They are not at all the same space. They might not even be in the same Rn. And we'll look at an example real quick here. And in fact, I think that's what I'm going to do next. But let me just tell you that since they are the same for any matrix, the dimension of the row space is the same as the dimension of the column space. We have a special name for that number. This dimension is called the rank of A. We might say rank parentheses A. Okay, so what is the rank of A? It is the dimension of the row space of A, which is the same as the dimension of the column space of A. All right, let me do an example now that puts all this together. And we will begin to notice some very interesting connections between the M and the N in an M by N matrix, and how that relates to vectors in Rn and vectors in Rm. Okay, so my example is, right here. Example, let A equal this matrix 1, 5, 2, 10, 1, 5, 2, 10, 2, 12, 6, 54, 2, 12, 6, 54, 3, 18, 6, 72, 3, 18, 6, 72, and 1, 5, 2, 10, 1, 5, 2, 10. Okay, this is a 4 by 4 matrix, right? Okay, I want to find a basis. Basis for row space. Basis for column space. And find the rank of A. Let me see if I can find something that doesn't squeak quite as much. We'll see what this does. All right, so all I'm going to do is I'm going to row reduce, and we'll see where that leads us. It's probably all going to squeak no matter what I do. 1, 5, 2, 10. I'm going to take -2 times the first row and add it to the second row. So when I do that, I get 0, 2, 2, 34. I'm going to take -3 times the first row and add it to the third row. That gives me a 0, and then a 3, and then a 0, and then I think a 42. And then I'm going to take -1 times the first row and add it to the last row. That gives me a 0, a 0, a 0, and a 0. Oh, okay, that dropped out right away. Didn't expect that, but okay. That's fine. I guess I didn't realize that the last row and the first row were the same, but that's okay. Okay, now what? Now I'll divide through the second row by 2, and then I'll use multiples of it, right, to go further. So let me keep this the same. I have 1, 5, 2, 10. Keep the top row the same. Second row is 0, 1, 1, 17. I'm not writing all my row operations out. I really like it when you do that so I can see what you've done if you make an error. I'm not doing that just to save time. And then let me just leave this as 3, 0. 0, 3, 0, 42, and then 0, 0, 0, 0. Okay. Let me go down here. So I have 1, 5, 2, 10, 0, 1, 1, 17. Take it times -3 and add it down, and I get 0, 0, -3. And then -17, -3 times 17 is -51. Add on a 42 and you get a -9. Okay, to save time and space, let me see if I can. Please rewrite this, but of course what I'm going to do is divide through by -3 here. And when I do that, I get a +1 and a positive 3. So please rewrite the matrix, with that step completed. Then I'll take, sorry, I got my row of zeros here, I can't forget. Then I'll take multiples of this, add it up, right? So I have my 0, 0, 0, 0, 0, 0, 1, 3. Take negative 1 times it, add it up. I get 0, 1, 0, 14. Take a negative 2 times it and add it up. I get 1, 5, 0, and that's 4, right? Yes. And lastly, I'm going to take this row times negative 5 and add it up. So rewrite it again, please. I'm not going to do it. If I take this times negative 5 and add it up, this becomes a 0. Negative 5 times 14 is negative 70. Add it on to 4, and I guess I get negative 66. Okay, and I have put it in. I've probably gone farther than I really needed to do, but that's okay. I've put it in reduced row echelon form, and that's, I guess, good for something I'm going to do later. But I've got it in a row echelon form. It happens to be reduced. And now what do I say? Find a basis for the row space. Answer is the non-zero rows. So let me rub this out. The non-zero rows right here. So it's 1, 0, 0, negative 66. That negative 66 is kind of funny. I may have made an error in my calculation. I hope not. If I made an error, you can fix it, I'm sure, but I don't think I did. 0, 1, 0, 14. I'm running into my matrix here, but the last one is 0, 0, 1, 3. Okay, there's a basis for the row space. Basis for column space. I hate this squeaking. I'm going to rethink this technology. The squeaking is just absurd. Basis for the column space, then, I look at, well, I know this much, don't I? I know that it's going to have 3 vectors in it because the row space basis has 3 vectors. The row space is a 3-dimensional vector space, and so the column space has to be a 3-dimensional vector space. And the way I get it is I go look at the pivot columns, which is the first, second, and third. So I go back to the original matrix, and I use the first, second, and third columns. So I'm going to have 1, 2, 3, 1. 5, 12, 18, 5. And lastly, 2, 6, 6, 2. There is a basis for the column space, and the rank, of course, is 3 because the number of vectors in the basis for the row space is 3, which of course is the same as the number of vectors in the basis for the column space. And so that's by definition what our rank is. So the rank is 3. And let's see, I want to say anything else here. I had something else I was going to point out. Well, all right, while we're here, let's find a basis for null space. Okay, so come over here and try a different marker again. I think maybe the problem is these markers get, after they've been used for a while, they get real squeaky. Let's do something we haven't done yet, separate from all this. Seemingly separate. Oh yeah, that's not as bad. Find a basis. Yeah, I think the markers need to be newer, then they don't squeak as much. Find a basis for the null space of A. All right, well, I have here what? I have 3 pivot columns, so I have 1 non-pivot column. So X4 is free. Let's say it's equal to T. Okay, then, so I know right now that the null space is going to have dimension 1, right? Because there's 1 free variable. So what am I going to have? I'm going to have X1 is 66 times X4, so it's 66T. x2 is going to be negative 14 x4, and lastly, x3 is going to be negative 3 x4, so negative 3t. So a basis there is, let's see, the null space of A is this set. It's t down here, then negative 3t, then negative 14t, then positive 66. T, for t an element of R. All right, and so that's equal to the span. So basis is, I'll just say, a basis, of course, is just this one vector, the set of one vector, 66, negative 14, negative 3, and 1. All right, when we pull out the t that we're multiplying by. Okay, I would like to point something out to you now. So A is a 4 by 4 matrix, correct? So when we take a vector x over to ax, we define the linear transformation of multiplication by A. That's taking R4 over to R4, isn't it? Now here's something I want you to see, and we will see this come up again and again. In this case, the numbers are the same, so it's a little bit more subtle, but we'll see examples where that's not true, and then it may be even clearer. But this is my starting vector space. Can you see that the rows really sort of represent being over in the starting space? So the row space right here should be thought of as a subspace of that R4. But the column space, that's the range of the linear transformation, that's sitting over here. So these vectors, these really represent, this basis is for a subspace of that R4. And the null space refers to all the vectors over here that go to 0, right? So the null space, of course, comes over here and belongs in R4. And notice something. I have one vector in the basis for the null space. I have 3 vectors in the basis for the row space. If I add those vectors together, the number of them together, 3 and 1, I get 4, the dimension of my starting space. That's going to turn out always to be true. And in fact, I guess I will go ahead and say that. It's what you're sort of doing is it's kind of like this. It's kind of like, what does the linear transformation does? It takes a vector and transforms it. One of the ways it might transform it is it might squish some of it away to 0, correct? So I start with all possible 4-dimensional vectors over here, and it turns out along one dimension in R4, those all get squished to 0. All the rest of them don't get squished to 0, and they give me a 3-dimensional subspace of R4 over here. So it maybe kind of makes sense that the range of the linear transformation, which is a basis for the, for the row space, a basis for the column space is a basis for the range of the linear transformation. The number of vectors there is exactly equal to the number of vectors in a basis for the row space. So when I think of the range of this linear transformation, I can think of how many vectors are there in the row space that would that number is the same number as the dimension of the range. Okay, so I started to say it a minute ago, and here I've got myself kind of tied up. Think of it like this. I collapse along one direction, one vector, and I have 3 directions left over here to come up in the range. So it kind of makes sense, I think, that if I look at the dimension of the range, which is the same as the dimension of the row space, and the dimension of the null space, and if I add those dimensions together, I should get the dimension of my starting space. It accounts for what happens to all the vectors. Some of them get squished away to nothing, and the rest actually contribute to the range. That's what I'm trying to say. Let me look at a little bit more explicit example. So let me just summarize that. So if A is m by n, then that means that I'm taking Rn to Rm when I do multiplication by A, right? The rank of A plus the dimension of the null space of A will equal that n, the dimension of the starting space. This represents how much of the starting space gets crushed to 0. This represents how much of it gets spread out into Rm. All right, so the sum is equal to the starting dimension. That is a big thing to remember. Let me do another example. We'll do a bigger matrix, but we'll already have it in reduced echelon form. And we'll see what's going on. And you know, again, this should make sense because now that we know that this is the number of pivot columns in A, and this is the number of free variables, which is the number of non-pivot columns. And how many columns do you have total? N in an m by n. So the number of pivot columns plus the number of non-pivot columns has to equal the total number of columns. So that's another way maybe to see it real quickly. Example, B is, what is it? It's 4 by 7. And what do I have here? I have the reduced row echelon form. If you put this in octave, if you put B in octave, the reduced row echelon form of B is 163 0204. 0001 0001 400 400, and then 0000019, and then all zeros. Okay. Basis for a row space. You can write it out while I'm rubbing this out. Write out the basis for the row space. Write them as column vectors. We could write them as row vectors, leave them horizontal, but it's just kind of natural for us to write vectors vertically as columns, so you rewrite them as column vectors. The basis for row space of the original matrix B. So I'm started off with something else, right? And I maybe put it in octave, and it gave me this back, all right? And my basis for the row space is, look, the non-zero row is right here. So it's 163 020 4 000 1400, and 5 zeros, and a 1 and a 9. Okay, that is a basis for the row space of the original matrix B, and that is a subset, the row space, or this basis is a subset of R7, right? That's where I'm starting from. If I think of multiplication by this matrix, think of the linear transformation as multiplication by this matrix. So right away I can tell you the rank is 1, 2, 3, is 3. But let's do a basis for, I guess I do a basis for column space. The answer is, I can't write it out because I don't have the original matrix. I need the original matrix, but I can tell you this much. It's the first, there's a pivot there. No, no, there's a pivot. So fourth, not a pivot. There's a pivot. That's sixth columns of the original matrix B. Original matrix B, right? So this is, I want a basis for a column space of B, of the original matrix B, and the answer is whatever the first, fourth, and sixth columns were of the original matrix. I don't have them here, and I'm not going to write them out. So that's it. That's easy. And let's see. What about the basis for the null space? First off, I will tell you, notice that it's a subset, that the column space is a subset of R4, correct? So it's a little bit amazing that I'm going to have 3 vectors here because I have 3 vectors up here. I know from 3 vectors up here, I'm going to have 3 down here, even though we're in totally different spaces, right? These came out of R7, and these are coming out of R4. But the vectors are different, very different. The vectors here are going to be in R4. There are only going to be 4 entries, right? So it's going to be very different from what we have up here, but the number of vectors in the basis for each is the same. Basis for a null space, I don't think I'm going to do it, but I'm just going to say right now I can tell you dot, dot, dot. You can go through and get it. What's the dimension of the null space? We should be able to get that real easily. Look, n is 7, and the number and the rank here is 3. This is the rank, right? I didn't say that, but the rank is 3 because that's the number of vectors in a basis for the row space, and it's also the dimension of the column space. So the answer is 4. There are going to be 4 vectors in the null space, and there'll be a subset of R7 again, correct? So there you see again, I have 4 dimensions of R7 being collapsed to 0. There are 3 dimensions, so to speak, left over, and that's what gives me a 3-dimensional range down here in R4. All right. So, yeah, all right, you should be able to work that through. And you can see I've got 3 pivot columns here, so I'm going to have 4 non-pivot columns. I'm going to have 4 free variables, so I'm going to have 4-dimensional null space. You can see it that way, right? But you know right away, because the number of columns is 7, and I have a rank of 3, so I better have a null space will have dimension 4. We sometimes call it the nullity of the matrix. All right, let's see. Yeah, I'm not going to work through. I have written out here what the basis is for the null space, but I'm not going to bother to do that because that's just pretty routine. Okay, so this is a big thing to remember right here. And then I also say, please read the extension of the invertible matrix there on page 237. I'm not going to talk about it right now, but it takes all the things you know about an invertible matrix and it now adds some things to it. So if you have an n by n invertible matrix, then guess what? If the rank is n, that would mean the null space would have to have dimension 0 because n plus 0 has to equal n. So you're going to have an invertible matrix. So it adds new ways to think about invertible matrices to our list of things. And so you can go back and figure out how to add the new things onto that monster if you want that we did in another lecture. But I'm not going to take the time to do that, but please read through those. You should know what they are. You may see them come up on a quiz or a test, so I'm going to just let you work on them. Now, what I want to do, though, is work a few homework problems, if you don't mind, from the text. And you'll see how we can learn a lot now from a matrix. Just by knowing a few facts, we can take our knowledge here and add a lot to it. So I'm on page 239. Number 6. Number 6 says 6 by 3 matrix A has rank 3. So A is 6 by 3. Rank of A is equal to 3. Find the dimension of the null space of A, the dimension of the row space of A, and the rank of A transpose. Okay, if it has rank 3, here's something that I didn't point out, but If you think about what the ranks of a matrix can be, the lowest it can be is 0. If it's just the 0 matrix, then its range is going to have 0 dimensions. Its row space will have no non-zero vector in it, so they'll all be 0, and so the row space is just the space spanned by the 0 vector, which is just 0, and we say that that's 0 dimensional. Okay, but the highest a rank can be, so the lowest it can be is 0, the highest a rank can be is, since it's equal to the number of pivot columns, it can never be more than the number of columns in a matrix. Since it's equal to the number of non-zero rows in the row echelon form of the matrix, it can never be more than the number of rows. So the largest a rank can be is the smaller of these two numbers. So here we see that the rank is 3, so it's, you know, it's hit its maximum limit there. Okay, now what does it say here? It says, find the dimension of the null space of A. Well, dimension the null space of A. Look, plus the rank better equal n, and what is n? Excuse me. 6 is the number of rows, 3 is the number of columns, so this is m by n. So it has to equal 3. So the dimension of the null space of A is 0. So this does not wipe out any vectors. It starts in R3 and goes to R6, multiplication by A does. So it doesn't collapse anything over here and just dumps it all into R6. That's the dimension of the null space. Dimension of the row A, well, dimension of the row space of A is what the rank is. So there you go. And then lastly, the rank of A transpose. Well, here's another fact. Rank of A transpose is equal to, if we flip everything and we do row operations, everything comes out to be exactly the same in terms of the dimensions of the null space and of the dimensions of the column space. So the rank of A transpose is equal to the rank of A, which is 3. So there's a general fact, and in this case, you get that the answer is 3. That's number 6. Let me try, try number 8. Number 8, suppose A is 5 by 6. So A is 5 by 6. Now it says, so it's m by n, so it's, you know, it takes R6 to R5, right? Multiplication by A does that. I like to put that up there to help me think. It has 4 pivot columns, so its rank is 4. So I'm taking R6 and squishing it into a 4-dimensional subspace of R5. That's what I'm doing. What is the dimension of the null space of A? I get a 4-dimensional space out, but I started with a 6-dimensional. 4 plus what gives me 6? The answer is 2. So dimension of null space of A has to be 2. I squished 2 dimensions away and got 4 dimensions left over being dumped into R5. What is the dimension? Is column A equal to R4? Why or why not? Okay, that's a good question. The dimension of the column space of A is the same as the rank, which is 4. So over here in R5, I'm looking at a 4-dimensional subspace of R5. Is it R4? The answer is it isn't exactly R4 because it's sitting in R5 and it can be sitting, it's not R4 because R4 would only give you vectors with 4 entries, right? In R5, you're going to get vectors with 5 entries. The thing is, you're going to have only 4 of these will be needed to span the range of multiplication by A, right? Only 4 of them are in the basis for the column space of A, but it's not the same as R4, correct? If those of you who had any more algebra would know, we could say it's isomorphic to R4, but it's not the same thing as R4. So the answer is no. Let's see, I'm just going down the line here. Look at number 10. If the null space of a 7 by 6 matrix, so right now I'm taking R6 to R7, correct? This is number 10. If the null space is 5-dimensional, what is the dimension of the column space? If the null space is 5-dimensional, I collapsed 5 dimensions here. I only have 1 being dumped over into R7. The rank is 1, so the dimension of the column space is 1. That's how to think about that. Number 12, if the null space of a 5 by 6, so if it's a 5 by 6, I'm taking R6 into R5. I'm going to have to collapse at least 1 dimension. And what does it say? Number 12 says, if the null space is 4-dimensional, what is the dimension of the row space of A? I collapse 4 of these dimensions over here, and I have 2 left over that get dumped into be the range over here. The row space is 2. Looking at that 6. 6 minus 4 is 2. Number 14, if A is 4 by 3, number 14, A is 4 by 3, so we go from R4 to R3, multiplication by A. And if it's a 4 by 3 matrix, what is the largest possible dimension of the row space? Well, okay, there we go. It's equal to the smaller of the two, the number of rows and the number of columns. So the smallest, so the largest it could be is 3, right? Because I'm dumping it into R3, you can see it there. The largest it could be, if it's a 3 by 4, what is the largest possible dimension? Again, the answer would be 3, because it's the smaller of the two number of rows and number of columns. Is the largest you could have for the rank. All right, let's see. Number 16. Number 16. I really like it. A is 6 by 4. So we are taking, multiplication by A takes R4 to R6, correct? Did I do that right? No, yeah, it takes R4 to R6, that's it. What is the smallest possible dimension of the null space of A? Look, I have R4. Do I have room to dump all of R4 into R6? The answer is absolutely yes. So I don't have to squeeze away any dimensions over here. So the smallest possible dimension of the null space is 0. If I were going from R6 to R4, I have to, dumping 6 dimensions into 4, I have to squeeze away at least 2. So the smallest, so the smallest dimension of the null space over here would have to be 2, correct? And another way to see that in terms of the language you've been using, the rank can be no more than 4. And so I have 6 minus the largest rank of 4 gives me the smallest possible value for the dimension of the null space, which is 2. Okay, but I like to think of it in terms of, hey, going from R6 to R4, I got to squeeze out at least 2. You know, if I don't even fill out of R4, if I only fill out a 3-dimensional one over here, then I must have squeezed away 3 dimensions, and the null space must have dimension 3, right? That's, I like to think of it in terms of the mappings and how things get squeezed. Let me do one more, let's see, let me do maybe 2 more, I don't know. Number 22. Yeah, I want to look at 22, and then we will stop here. Well, okay, I think I'm going to do 2 more, 22 and 24. I wanted to run through those very quickly. You might need to go back and replay them. I didn't write them all out, I just spoke them. But I'm hoping you can write out what I said. I'm just trying not to make you have to sit here and watch these videos any more than you need to. So I don't want to just spend a lot of writing if it's something that I think I can summarize quickly just by speaking. Number 22. I want to look at that one a little bit more, though. Is it possible that all the solutions of a homogeneous system of 10 linear equations in 12 variables are multiples of one fixed non-zero solution? Discuss. All right, it says a homogeneous system. So I'm looking at this. If I write it in matrix form, I'm looking at a homogeneous system. And it says 10 equations, 12 variables. So look, the system looks like this. There are 10 of these and, 12 of those. So A is 10 by 12, isn't it? So A takes, the multiplication by A, meaning x going to AX, takes R 12 into R 10. All right. Okay. Now, I can tell you a number of things now. I don't know what the rank is. Right? We'd have to have the matrix, we'd have to put it in echelon form and see how many non-zero rows we have or how many pivot columns we have. It'll be the same number, right? One's the dimension of the row space, one's the dimension of the column space. They'll be the same. Although the row space sits in R12, the column space sits in R10, and the null space sits in R12. Okay, so I can tell you a few things here. I have to squeeze away at least 2 dimensions to get over here to R10. It might be that the dimension of the column space is a lot less than 10, in which case I'm squeezing a lot more dimensions out over here. But I have to squeeze at least 2 dimensions out over here to get over here. Okay, now read what it says. Is it possible that all solutions of the homogeneous system, so I'm looking at all possible solutions here that go over to here, where this is really 10 entries, right? And X is 12 entries. Okay. Is it possible that it's multiples of one fixed non-zero solution? In other words, what does the null space look like? Is it multiples of one solution? That's asking this. Is the null space of A, or could the null space of A be one-dimensional? That's what it's asking. All solutions be multiples of one fixed solution means there's one vector that spans it all. And when it's written like that, you can see the answer is absolutely no, because I have 12 here and I'm going to 10. No, null space of A is at least 2-dimensional, isn't it? Might be more, but it can't just be one. It can't just be one. It could be if this were R11, if there were 11 equations, but there are only 10. All right, one more, and then I promise I will stop. Number 24. What I'm erasing here is the key thing to remember, right? The dimension of the null space of A plus the dimension of the row space of A is always equal to n, where n is the number of columns. Or it's the dimension of your starting space when you're thinking of multiplication by the matrix as a linear transformation. Dimension of your domain space. Okay, number 24. Yeah, the more I use this, the more it squeaks, so need new markers. Is it possible for a non-homogeneous system of 7 equations in 6 unknowns? So I'm looking at that non-homogeneous, where B is not 0, and it says 7 equations, 6 variables. All right, so what do I have? I have 7 rows, 6 columns. So A is 7 by 6. The multiplication by A takes R6 to R7, does it not? All right. So X has 6 entries, it's in R6. B has 7 entries, it's in R7. What does 24 say? It says, is it possible for a system 76 to have a unique solution for some right-hand side of constants? Is it possible for such a system to have a unique solution for every right-hand side? Okay. It's asking, is it possible that there's a unique solution for some particular B? And then it's asking, is it possible that there could be a unique solution for all B? I think actually the second question might be a little easier to answer. Is it possible that I can always solve this for every B? Well, for every B, I said B is an element of R7. Right? So if I look at all possible B's, I fill out all of R7. Right? The rank of A can be no more than the smaller of the number of rows or the number of columns. So it's less than or equal to 6. Okay. So that says, so the dimension of the column space of A, which is the dimension of the range of the linear transformation, is definitely less than 7. So I can't get everywhere in 7. So AX equal B is not consistent for every, for at least some B. Let's say it like this. It's not consistent for at least some B in R7. Let me just reiterate that. I'm starting in R6 and I'm going to R7, right? And I'm using, this is a linear mapping. There is no way to fill out R7 when I'm starting with just 6 dimensions. My rank is at most 6. I can't get a 7-dimensional output. I can't get up to R7. I'm going to have a proper subset of R7. So it's not consistent. So the answer is no for the second one. Is it possible for a non-homogeneous system to have a unique solution for every right-hand side? The answer is no. We're not going to have a solution for some right-hand sides. Now, is it possible to have a unique solution for some right-hand side? The answer is, look, if I, for some right-hand side, we should be able to solve this. If the rank of A is equal to the max it can be, which is 6, then the dimension of the null space of A has to be 0, correct? It has to be 0 because I have 6 columns. And if the rank is 6, what I've done is I've taken all of R6 and I've dumped it out in every possible way in R7. I've squished nothing down. The dimension of the null space is 0. So, in this case, if AX equals B has a solution, it's unique. Because how do we get all solutions? You give me one, and then I add to it all the solutions of the homogeneous system. That's we did 2 months ago. You add all the solutions of the homogeneous system to one solution of the non-homogeneous, and that gives me all possible solutions of the non-homogeneous. So if the rank is 6, there are nothing but the trivial solution. The dimension of the null space of A is 0. There's nothing but the trivial solution to the homogeneous case. So I have nothing more to add to my one solution. So if I have a solution, then it's going to be unique. But of course, for some B, I'm not going to have a solution, right? Because the rank is not big enough to fill out all of R7. Okay, homework. Yeah, time to stop. Homework. Page 238 is where it starts. I say 1 through 25 odd. Probably 1 through 15 odd is what you might get quizzed over. These latter ones take a little more thought, and I'd like you to really work on them, but maybe for the quiz tomorrow, I wouldn't hold you responsible for anything beyond number 15. So I'll just say that, I won't write it down. All right, I'm getting done about 44 seconds early, so yeah, 44 seconds less than a 50-minute lecture. See you tomorrow. Bye.